This week, we have the pleasure to have Zeev Rudnick, who will talk to us about the Robin eigenvalue problem. So, Zeev, the floor is yours, and thank you very much for being here.
Okay, thank you all for coming. So I will be speaking about something that most of the audience is much more of an expert than I am, or rather is an expert while I'm not, but because the Robin eigenvalue problem has been a constant feature in this seminar, and I will be speaking about something that I've been doing with Igor Wigman from King's College London and Nadav Yesha from Haifa, whose mugshots you can see here. And it's very new stuff, so I'll be happy for any feedback. So the context of this lecture is on planar domains. So we talk about planar domains like the one you see here, which is a bounded domain with a piecewise smooth boundary. I would make it smooth, except I need to allow corners for some of what I'm doing, but otherwise smoothness is part of it. And we are interested in eigenfunctions of the Laplacian on the domain with either Dirichlet or Neumann, or more importantly for us, Robin boundary conditions. So this is the Robin boundary condition for people who haven't seen it. So we take the normal derivative in the direction of the outer pointing normal, like in this picture, and we want it to be proportional to a negative multiple of the function on the boundary. So if this constant is 0, then you get Neumann boundary condition. And the limiting case is of the Dirichlet boundary condition, where you ask for the function to vanish on the boundary. Formally speaking, that corresponds to sigma equal infinity. I can also make this constant actually vary on the boundary. And most of the results I have are valid in that context as well, but it will simplify the discussion if I just take it to be constant. And a standard part of the theory says that for a bounded domain with a reasonably smooth boundary, there are actually eigenvalues, and there's a discrete set of them which only accumulate at infinity. If we want a Dirichlet boundary conditions, I don't need smoothness, but with Neumann boundary conditions, it's more delicate. So Lipschitz is fine for discreteness of the spectrum. And if the Robin constant is non-negative, then all the eigenvalues are also non-negative. And that's what I will be assuming throughout the talk. Okay, so just again, for people who haven't seen it before or need a reminder, let's discuss the one-dimensional case, which should be completely trivial. So in the one-dimensional case, we're looking at an ordinary differential equation. So we want the second derivative to be proportional to the first, and then the solutions are linear combinations of sine kx and cosine kx, and k can be anything. Once you put the boundary conditions, k is quantized. So if you take Neumann boundary condition, then the frequencies, these k's, have to be integers, or integer multiples of pi, and the multiples can be any non-negative integers, and the corresponding eigenfunctions are just cosines. So this is completely solvable. In the Dirichlet case, it's very similar. The eigenfunctions are sines. Those are the ones that vanish at the edges of the interval. And here the frequencies, again, are integer multiples of pi, but here you need positive integers because you can't take n to be 0. You'll just get the 0 function. So you just get one less eigenfunction in the Dirichlet case. In the case where the Robin constant is non-zero, not infinity, the eigenfunctions are again simple. They're just linear combination of cosine and sine, where the coefficient is dictated by sigma. But the eigenvalue itself is some transcendental quantity. It's given by the solution of the secular equation, which you see written here, that the tangent of k is some rational function of k, and it doesn't have any closed form solutions. Here you see a plot of it. So tangent is the blue curve, and the rational function of k is the yellow curve, and where they intersect, this corresponds to frequencies, the square root of the eigenvalue. Okay, so this is again standard theory for people who know. Now, if we go back to 2 dimensions, as I said, there's a discrete set of eigenvalues, and Weyl's law says that the number of eigenvalues grows linearly as we increase them, and the constant has to do with the area of the domain. So in some special case, you can reduce it to counting lattice points. Usually it's the eigenvalues are purely transcendental, as we saw in the 1-dimensional case. Now, this is the main term. This was Weyl's law, which is over 100 years old. Weyl's conjecture, which many people have mentioned in this seminar, says that if the boundary is sufficiently smooth, then in the case of Neumann or Venn boundary condition, there's a secondary term which comes with a plus sign. The secondary term is root x multiplied by the length up to some normalization. And for Dirichlet boundary condition, again, there's a secondary term, but which comes with a negative sign. And this, as far as I know, is still open in generality. There's the famous work of Victor Ivry that says that under an aperiodicity condition on the billiard dynamics, which I'll describe the billiard dynamics a little later, then this conjecture is valid. And for instance, it's known, the condition is known for domains which are real analytic, or in the piecewise smooth case, if the boundary is concave. It's not clear to me whether to believe that this condition, which I didn't say, I will say it now, whether this condition is always valid. So the condition is that the set of periodic orbits of the billiard in phase space has 0 measure. This is not so easy to check. Anyway, it's not, to my knowledge, it's not known if it's always valid. I recently heard a lecture by people working in dynamics where they had a program to construct a counterexample, but as far as I know, they haven't succeeded yet. So I don't, as far as I know, the conjecture is open. It may be valid even without this aperiodicity assumption, but I just don't know what the situation, what's the state of the art as of now. So I will need to use this conjecture, not really use it, to show how it can be used a little later. Okay, so now I come to the subject of the lecture, which is the Robin Neumann gaps. So one thing we know about the Robin eigenvalues is that they are monotonic as a function of this boundary parameter. So in particular, the nth Dirichlet eigenvalue is always bigger than the nth Neumann eigenvalue, and the nth Robin eigenvalue always lies between them. So the nth eigenvalue is monotonic as a function of sigma, of this boundary parameter. And the conclusion is that we have a positive gap between the nth Robin eigenvalue and the nth Neumann eigenvalue. And the fluctuations and limiting behavior of this quantity is what I want to discuss, because I haven't seen this in the literature. So I should say that initially, when I started getting interested in this Robin eigenvalue problem about a year ago, I had completely different ideas in mind. I was reading a paper of Uzi Smilansky and Martin Zeev and Rudnick, I think, about these, and the paper of Michael Berry and Mark Dennis that Marco Marletta mentioned a few weeks ago, that was looking at completely different things, but I got diverted by this question. So what I want is to discuss these Robin Neumann gaps, the statistics and limiting behavior of this quantity, the difference between the nth Robin eigenvalue and the nth Neumann eigenvalue. Okay, so what I'm going to show you now are the results of a few experiments that we have carried out. Okay, so I'm going to show you about 6 domains, and for each of them, I'm going to show you the Robin Neumann gaps. So in each of these pictures, you see a lot of blue dots. So the blue dots are just these Robin Neumann gaps. So for instance, for the square, you see here plotted 2,000 of these Robin Neumann gaps. These are the blue dots here and here and here. So the 1,500 Robin Neumann gap is maybe this blue dot. Okay. Here's the same picture for the unit disk of, again, 2,000 of these, the first 2,000 Robin Neumann gaps. You clearly see a different behavior altogether. Now, in each of these pictures, there's a red line and the green curve. So the green curve is the running average of these gaps. So you see it over here. So I took the first n gaps and looked at the average, and then computed this average as you increase n. And that's the green curve you see over here. And there's a red line. The red line is a theory. The green line is an experiment. The green curve is an experiment. The red line is a theory. And in all the cases you see here, there is clearly a convergence of the green curve to a red line, which means that there is a limiting mean value. Okay, so this is for the unit square and the unit disk. Now, both these cases are separable. The unit square, I sort of showed you what you need to do. We did the one-dimensional case, and then you just look at the superposition of 2 such things. So to compute 2,000 eigenvalues is trivial. All you have to do is to solve this transcendental secular equation that I showed you before. You solve it numerically. I don't have any explicit solution. This is the picture that you get. It's not completely trivial to analyze it, but numerically it's quite easy to do. For the unit disk I'll describe later, as is well known to everyone here, at least in the Dirichlet case, you have separation of variables. So you get an ODE which you need to solve. I will discuss it later. Now let's turn to more exotic examples. So the first example is an L-shaped billiard, which I got from taking 3 congruent squares. So it's a very symmetric L-shaped billiard. And Wei-Tu Bao and Li-Zen Chen, who's here yesterday, sent me a computation of 10,000 of these eigenvalues. So these are the black dots. And again, you see the green curve, which tends to this red line. I will tell you what the red line is in a few minutes. Here's another example of a mushroom billiard. which you get by putting a semicircle on top of a rectangle. Again, there's a reason why I'm doing this. Now, in this case, we meaning Weyl and Ligen, haven't yet started working on it. So all I have is 200 eigenvalues, which I generated, we, not I, Nadav, Ego, myself, with the help of a finite element package. But with the finite element package, 200 eigenvalues is the most you can expect to get. You start getting garbage afterwards, and I'm not even sure of 200 here. But you see a pattern, and again, you see a green curve tending to a red line, which is the only reason I believe these numbers. Okay, you also see several other things, which I will come back to. And I will show you two more pictures. The first is of the stadium billiard. So you take a rectangle and put two semicircles at the edges. Here I've desymmetrized it, so you get a quarter of a stadium. And again, you see those blue dots and the red green curve, which looks like it's tending to this red line. And here, again, I only have 200 eigenvalues with some unknown accuracy using this finite element package. And the last picture is of a dispersing billiard. So if you look at this picture, you take 4 disks in the plane and look at the bounded part of the complement. So this is a concave billiard with a smooth boundary, and there's a reason why I chose it. So both of these examples, the billiard flow is ergodic, but they're not identical. They have some different features. So in any case, you clearly see the green curve turning to the red line, but there's also other features that I will share with you now. So these are the experiments, and I want to explain as much of these experiments as I can. Okay, so now is a good time to ask questions before I actually turn to a description of the results. Okay. So the first result that I alluded to is that the green curve actually tends to a red line. And the statement is that the mean value, there is a limiting mean value of these Robin and Neumann gaps. And the answer is that it's twice the length of the boundary divided by the area integrated along the boundary in some sense. So times this Robin constant sigma. Okay, so that's the red curve, and I think you've seen 6 pictures. This theorem is clearly true in the sense that it's true experimentally, and we can actually prove it. So I will maybe briefly describe the proof later on. So one immediate corollary is that these gaps are all positive. So if they have a finite mean value, it means most of them can't be very big. So for instance, almost all of these gaps, the nth gap is usually less than log n, or log n, or anything that you want. Okay, this is a tautology, this corollary. Once you have that positive sequence of positive numbers has a finite mean, then most of them are bounded.
Zeev, and the thing on the right is the largest for the disk, right? The constant by the isoperimetric.
Yes, that's true. That's a true observation. Thank you for that. I don't know the significance of that.
Well, so probably this limiting thing is going to be, the disk is going to be extremal for this for this kind of eventual gap, right? That's what you proved.
Yes, but I understand what you're saying. It's correct. I have a conjecture for the disk. What you say may be relevant.
Okay.
But this is an interesting observation. Okay, so this is statement number 1. Again, this was clear from the pictures. it's something like this is true. The only question is how I knew how to where to put this red line, and this is how I just knew the answer. The second result is again obvious from the pictures. Here is a picture for the disk. There's a forbidden region here. There's a forbidden region, which means that the Robin and Neumann gaps are bounded below by something. In the picture, in all these pictures, it's clearly true. Now, unfortunately, right now, we only know how to do it for star-shaped domains. So this is not a star-shaped domain over here, because it turns out that for all points in the interior, there is another point where if you try to connect them by a straight line, you exit the domain. That's the definition of star-shaped. So in particular, convex domains are star-shaped, but you can, for instance, an annulus is not star-shaped, this isn't star-shaped. So the theorem says that if the domain is star-shaped, then there's a uniform lower bound for these Robin-Neumann gaps. I don't think the star-shaped condition is necessary.
Can you find a constancy which is valid for any convex domain, say? The same constancy?
No. So the constant, first of all, depends on sigma.
Yes, but
we think it's linear. It's probably linear in sigma. And then you would be asking if the prefactor. I don't know. I don't know.
Okay.
I understand. It's a good question, but I don't know. I don't know. If we look at the examples, let's go back to the examples. So you probably have to measure it in the right units, maybe divide by the mean value or something. And I don't know the answer, whether how it depends on the domain, and whether it's got a uniform lower bound, or to go back to Dima Jakobson's question.
Please, I have just one question.
Yes, please.
Concerning this constancy of sigma, can you compute it explicitly in terms, or I mean, on the unit ball?
On the unit disk?
Or unit disk, let's say, yes.
Yeah, on the unit disk, I don't know the answer to that, but I suspect that it can be done. I don't immediately know the answer to that. There are many things on the unit disk which should be possible to do, but which we have not succeeded. So this is a good question. I suspect that the answer is yes, we can compute it, but I don't know. Right now, I don't know how right now.
May I make a comment?
Yes, Susie.
In this paper which you mentioned by Martin Sieber especially and all the other gang, we give a heuristic file formula, which is derived by the old methods which are used by physicists to derive it. And there are three terms involved: the volume term, the boundary term, and the curvature term. Now, the boundary term, if I look at it, then it gives you result because you are looking at the average number function. And the next term includes an integral over the curvature of the boundary. And that might give you an idea of the result, although of course it is not, we don't yet know because of Ivry's famous theorem if the third term in the Weyl formula holds. However, experimentally it holds very well for sufficiently smooth boundaries, including concave, convex, and whatever, because this is taken into account by this integral.
Right, so the way we do it is not exactly by this method. So this might give you an answer, a better answer for the lower bound. We do it by somewhat different method. Okay. In particular, because I wish I was able to use a trace formula here, but the trace formulas that we can handle, I don't know how.
We do have a trace formula which is again heuristic. You know, we are doing it without caring about all the little things. But as you also know, it works.
Good.
So actually, your result.
Conjectural heuristic argument, and that can be checked against the data, because here you can generate data. This is
Right.
the thing.
So in fact, in the estimate, you don't assume any condition on the mean curvature of the boundary, right?
No, nothing. It's got to be piecewise smooth. It's got to be piecewise smooth, and this star-shaped condition, which should not be necessary, but that's it. I don't assume anything about the curvature. Like this domain with negative, positive curvature. A rectangle is also good, where you have zero curvature. The stadium is good, where you have parts with zero curvature, parts with positive curvature, and so on. Right, so a good question is, what can one say about the exact value of this lower bound? You can clearly test it against numerics. And the question that I have for the experts here, whether you can remove the star-shaped condition. I'm sure it's possible. It has to be someone who actually is more knowledgeable than ourselves. Okay. So the next question, so I discussed mean value, I discussed lower bounds. The next question is upper bounds. Which again, this is, Uzi, you should stop listening, because this is the kind of thing that only a mathematician would try to go for, because the kind of thing you can prove is clearly so much worse than the truth. So here is a way to get an upper bound, which is a stupid way, but I will explain it anyway. It's to use the two-term value that I mentioned, which Victor Ivry called. I don't think this is the right reason to use for the two-term value, but it can be used. So as I was telling you, there's between the Dirichlet and Neumann cases, there's a difference in the sign. There are less Dirichlet eigenvalues than there are Neumann. Particularly the nth Dirichlet eigenvalue grows like n plus a constant times root n plus lower order terms, while the nth Robin and Neumann eigenvalues grow as n minus multiple of root n. So the difference between the nth Dirichlet eigenvalue and the nth Neumann eigenvalue is exactly twice this term. So it's a multiple of root n. So the nth Neumann and the nth Dirichlet eigenvalue stay apart at the rate of square root of n. Now, if you use the Robin and Neumann results, then they have the same main and secondary term. That means that they differ by a lower order term. So you get an upper bound of little o of square root of n, which is a tiny bit better than what you know about Dirichlet-Neumann gaps. Okay, this is like the null hypothesis, so to speak. This is a trivial bound using a really non-trivial result. Okay, but we can do better. And how much better? Instead of the constant of a half, we can exponent a half, we can put exponent of 1/3. Okay, and here we need to assume that the boundary is smooth. I don't think it's necessary, but it's a failure of our technique. This is a bunch of initial results. I'm sure they can be improved by people with some expertise. So the result is that we have an upper bound of n to the 1/3. So 1/3 is better than 1/2. Proof is easier. So it's good in many cases. Okay, so I'm just repeating this. Upper bound of 1/3. And if you look at what's happening in the unit disk, you clearly see a lot of relatively big gaps. But I don't know how big they are. Now we can improve this 1/3. So the 1/3 is a universal bound. In a few special cases, we know how to improve them. For instance, for the unit disk, we can replace the 1/3 by 1/3 minus some small number. Okay, this is some kind of vulgar number. Whenever you see a number like this, then you've got to have some number theory in the background, because only people in analytic number theory are capable of producing such strange results. And a better result we have for rectangles, and for rectangles we have a uniform upper bound. So these are two special cases where we can do better than the general purpose bound that we have. A question that I don't know the answer to is whether there are any planar domain where these Robin Neumann gaps are unbounded. As I mentioned, for rectangles, they are bounded. If you look at the picture of the Robin Neumann gaps for the unit disk, if I were a betting man, I would say that they are not bounded. That there's, this sequence here is climbing to infinity. But I haven't been able to prove or disprove this for the unit disk. Nor am I able to give you any example of a planar domain where I can prove that the Robin Neumann gaps are not bounded. If we go away from planar domains and look at Riemannian surfaces and look at the Robin Neumann gaps there, there is an example of the hemisphere where we can actually do better, and there we actually understand there's a nice theory of the Robin Neumann gaps which you can cook up there, but in particular we can prove that in that setting the Robin Neumann gaps are not bounded for the hemisphere. But for planar domains, we don't know if there's any example. Okay, so these are the results that we have for upper bounds. So if I have time, I will want to describe the disk, the unit disk, where you get this strange exponent. So the last result I want to describe of a general nature has to do with the billiard dynamics. So for people who haven't seen this, what is the billiard dynamics? So you imagine the domain as a billiard table, and you play your favorite game of billiards. Like here you see Fast Eddie and Minnesota Fats playing billiard. So you take your cue ball and your billiard ball and take your cue and hit the ball. You assume that there's no friction and that you go at unit speed, and then it bounces off the boundary, and the angle of incidence equals the angle of reflection. That's the dynamics. So you get a dynamical system whose phase space is the set of all possible initial conditions and all possible directions of the boundary, and then you just get a flow on the space by hitting the ball. So that's a dynamical system. You can play it in a rectangle like Fast Eddie and Minnesota Fats, or you can play it on a disk or an ellipse like this guy here, which some of you may know. And this dynamics is the raison d'etre of the examples that I've chosen to display. So for the rectangle, the dynamics is integrable in a suitable sense, as it is for a disk. Here you see an illustration of this. For a disk, you start with the trajectory. It will be a straight line. That means it will be tangent to a concentric circle, and then the result is that all successive segments of this particular trajectory remain tangent to this same concentric circle, which you see in this example. It's called a caustic. And there's a similar and more elaborate result for ellipses. So these are integrable dynamics. Then there is another extreme, which I will describe a little later, which is of billiards in polygon in a stadium, or in this area here, which turn out to be ergodic. So I will remind people what ergodic means. And then there's a variety of intermediate cases. For instance, you can play billiard on an L-shaped domain or a hexagon, a regular hexagon. These are called rational polygons, and the billiards are similar to integrable, they're pseudo-integrable in a suitable sense. In particular, they're not ergodic, they're very regular. And there are intermediate cases like this mushroom billiard, where you have a mixed phase space where positive proportion of trajectories think that you are inside a circle, and therefore they look like sort of trajectories of circle, while a positive proportion of the trajectories think that you're inside a stadium, and then they're sort of chaotic. So for the stadium and for this dispersive billiard, we have chaos. In particular, you have ergodicity. So I'll just remind people what ergodicity means. It says that if you take a generic initial condition, if you take a typical trajectory, then the orbit is uniformly distributed in phase space. In particular, it's dense. So that means if you compute the time average of your favorite observable along this trajectory, then you will converge to the space average of the trajectory of this observable. This is for generic trajectories, not for all of them. Okay, so that's a definition of ergodicity. So as I said, the stadium billiard and this dispersive billiard are examples of ergodic dynamics. So the result that we have for ergodic billiards is that not only is there a limiting mean value, as there is for any reasonable billiard, any reasonable domain, but in fact for ergodic billiards, there is a density 1 subsequence of the eigenvalues along which the Robin and Neumann gaps converge to the mean value. Okay. And a question that I have is, for this dispersive billiard, I expect this result to actually be better. I expect that you don't need a density 1 assumption, that the nth gap actually converges to the mean value. And here you see the numerics, which are clearly clearly tell me that this cannot be correct. But the numerics are only of 200 eigenvalues, and therefore I don't know what to read of this in the limit. So we are working on generating several thousand eigenvalues. Once we have that, I'll be able to know if this conjecture is completely wrong or maybe it's correct.
Zeev?
Yeah.
If you take a stadium billiard, but not with parallel lines, because the parallel lines generate in the stadium that you have a family of what we call bouncing ball trajectories, which are not ergodic. They are the ones which are not, but they are dense. So if you remove them, you can remove them by taking what is now parallel straight lines to take them not parallel and then connect them with smooth derivative to the circles. Then you don't have them. Did you check that the same phenomenon still occurs? Or it goes back to the dispersing billiard case?
So the reason we looked at this dispersive billiard
is
exactly
to avoid,
because for that you don't have bouncing ball.
Right, good.
It's uniformly hyperbolic.
Good.
That's why I looked at this example.
Okay.
But right now I don't have numerics to tell me whether this is bullshit or not. But that's the reason why we looked at this dispersive example.
I think I can supply you some old numerics. Because this is the Sinai billiard, and we have done the Sinai billiard.
No, the Sinai has bouncing ball, as you know.
Yeah, but you can remove them.
No, but the removal, I don't know how it affects. So
Okay,
I
we
don't
will
know
speak
the
about
effect.
it. Okay,
Let's
good.
work with a cleaner system here. This
Good.
system is cleaner in the sense that you don't need to remove any bouncing ball modes. Now, of course, if you work out the theory when you have a negatively curved surface, but you have with a boundary, then there too you will not have bouncing ball modes. It will be a clean, uniform hyperbolic system. But I think anyway, I've not did experiment on that. Okay, so this is what we know and what we think is interesting to discuss about ergodic billiards. So let me just display two slides with one of the tools that we use, and one of them is a variational formula. This is I picked this up from a survey by Doron Bucco and other people. This is described as folklore. It says that you can compute the derivative of the nth eigenvalue, the first variation of the nth eigenvalue, in terms of the boundary data. So the nth derivative, the derivative of the nth eigenvalue with respect to this boundary parameter is the ratio of the norm of the square of the eigenfunction on the boundary to the total L2 norm of the eigenfunction. So there's a closed formula for it. Okay, and once you know this, then it tells you that we have a formula for the nth gap by using the fundamental theorem of calculus. So if we normalize the nth eigenfunction to have L2 norm 1, then the formula just says that it's the integral of the square of the boundary integral. So there's a parameter here. So the parameter here, you change the eigenfunction with the parameter, you integrate its square along the boundary, and then integrate or average it with respect to this Orban parameter. So it's a formula. But once you have this formula, you can try to use it to get upper, lower bounds on these L2 restriction norms. Okay, so it brings you back into a question that some people here have thought about a lot, which is restriction norms. Okay, so let's see an example of how to use it by proving the first result about the existence of a limiting mean value. So you want to compute this mean value, so you substitute the formula that we have, interchange, averaging, and integration, and summation, and so on. And you are left with understanding the average of these L2 restriction norms. And for that, you use a local Weyl law, which tells you in particular that there is a limiting mean value. So this is due to, I guess, Ozawa in the Dirichlet case. I looked at the paper and didn't quite understand what it says, but Steve Zeldich was here, and Andy Hassel worked it out in great generality. It's certainly in the case that we need, and they said that it's inside Ozawa for Dirichlet case. Anyway, so you use what is known about these L2 restriction norms and insert it into this variational formula, and out pops this limiting mean value. Okay. So if you know this, this is not complicated. Now you can also use it to try to prove the upper bound, but by again inputting something about the L2 restriction norm, and as a result, it's I guess due to Tatao from about 20 years ago, and rediscovered since, or maybe in better form by Barnett, Hassel, and Melissa Tacey, just a couple of years ago, that there is a uniform, you can give a bound for these L2 restriction norms as 1/3 of the eigenvalue to the 1/3, and not worry about the dependence on sigma. The nth Robin eigenvalue is always bounded by the nth Dirichlet eigenvalue, so that removes the dependence on sigma. And in the planar case, the nth eigenvalue grows like n, so you get a bound of n to the 1/3. So that tells you, that gives you this general purpose bound for the nth Robin eigenvalue, thus bounded by n to the 1/3. Okay. Now I should say that this bound here for the L2 restriction norm is sharp in the disk. So on the disk there are these whisper and gallery modes, and you can compute everything on the disk using what we know about Bessel functions, and it turns out that this L2 restriction norm bound is sharp on the disk. Nonetheless, on the disk we can do better, but we can do better not by using this bound, but by using something else. So this is the last thing I want to describe. Okay, so for the unit disk, we have a bound which is an exponent which is slightly better than 1/3. And to do that, you have to remember that on the disk we have separation of variables, and the eigenfunctions are given in radial coordinates as cosine sine and the nth j Bessel functions with a dilation, and the eigenvalue is the nth is related to zeros. In the Dirichlet case, it's just zeros of the nth Bessel function. In the Neumann case, it would be zeros of the derivative. In the Robin case, it's zeros of some linear combination of the j Bessel function and its derivative. So you get a result in terms of Bessel functions. Now on the disk, by using this, you can reduce the Weyl law on the disk to a lattice point counting. This was done by Kuznetsov and Fedosov in the 1960s and rediscovered by Colin de Verdier, who's here, I believe, and not that long ago. It's an involved thing. And in any case, it says that the number of eigenvalues up to x, which means you have to count zeros of the nth Bessel of this nth cylindrical function, this nth Bessel function. As you vary over all n and all zeros, you count how many of them there are up to x, and it reduces to counting lattice points in a dilate of this strange domain here that you see this picture. It has a formula, but the picture is that you take a domain, it has corners, it has cusps, it has flat pieces, it has curved pieces. It's kind of a mess if you like doing lattice point problems. So it's that number plus an error, which I would love to have smaller, but the proof, this is what it gives. And once you have that, you can try to apply what we know about counting lattice points. And in particular, if you have a good remainder on the lattice point problem, you will have a remainder term for the Weyl law. So that's, for instance, how you can try prove Weyl's conjecture for the disk. Again, this is because it's a very special system. And the way it works is if you have a remainder term for this lattice point problem, so the main term is always the area, and you have a remainder term which is some power of x, then it will give you a remainder term for these two-term Weyl law with the same exponent, as it turns out. The exponent, you can't do better than 2/7 by this argument, because you incur an error in reducing the Weyl law to the lattice point problem. So unfortunately, you can't get to what should be the truth, which is 2/8, 1/4. And in any case, it tells you that if you take the Robin and subtract the Neumann, they have the same main term, you get an upper bound of n to the theta, where theta is the best exponent you can get for this lattice point problem. Colin de Verdier gave an exponent of 1/3, which matches what we know for general purpose results due to van der Kolpert 100 years ago for smooth domains. This domain is not smooth, so it's much more difficult, but you get 1/3. So that will give you the same general purpose upper bound that I had before. So this is not good enough. But very recently, Guo, Wang, and Wang improved this by using sort of some more modern techniques in lattice point in analytic number theory, and they got a something better than 1/3. How much better doesn't really matter now. So that's how you get a result that's better than 1/3 for the unit disk. And again, for the unit disk, I believe that it's in some sense the most extreme case. I believe that these Dirichlet-Neumann gaps are not bounded, but I don't know how to do that. We do have an upper bound, which is better than what you can get in general. Okay, so let me just summarize what we did here. We studied these Robin-Neumann gaps, and we proved that there's always a limiting mean value. We gave uniform lower bounds under some strange condition, upper bound in the case of smooth boundary. In some cases, we improved it, like the disk or the rectangle. And for ergodic billiards, we can replace mean value, but by almost sure convergence. And for people who want to see more, there's a couple of preprints, recent preprints on the archive. Okay, and, thank you for your attention.
Thank you, Zeev, for this very nice and very rich talk. It's now time to ask questions or comment about the talk. Just unmute yourself and go ahead, or you can also use the chat, and I will give you permission to speak.
I have it's Yves Colin de Verdier. I have a question.
Yes.
Do you know something in the case where sigma is non-positive, the number of negative eigenvalue or something?
No,
like
I
that?
have not looked at that. I've not looked at that. I was sort of, I said this Robin eigenvalue comes from heat conduction problems, and there it's not physical to look at negative.
Yeah.
But I know there's a lot of people who are now angry at me here in this audience who have studied exactly this question that you've asked, in particular asymptotics, as sigma tends to negative infinity,
Yeah.
so on. But I have not studied. I've not studied what happens when sigma is negative. Most eigenvalues will be positive. There will be a few.
Yeah, of course, but still there's
I've not studied what happens.
Okay.
Because these results are asymptotic for large n. Therefore, in some sense, negative sigma.
Yes, I have another remark. In your you computed the derivative with respect to sigma, and maybe there are some degenerate eigenvalues, but it's still piecewise C1, or
again,
can you compute the
you're asking about this formula.
Oh, yeah, but still, if you have a degenerate eigenvalue, it's not C1, but maybe piecewise C1 or something like that.
Yeah, so here I try to quote this lemma very carefully. The formula works. You can put it any eigenfunction. So if there are many eigenfunctions,
okay,
then it still works, but it is no longer smooth.
Yeah.
The nth eigenvalue is piecewise analytic.
Yeah.
It comes from, as you know,
extremely
well, this Kato theory of perturbation.
Yeah.
So it's only piecewise analytic, but there are bifurcation points, and this is crucial. For instance, in trying to understand the disk, why I'm not able to prove or to disprove that these gaps are unbounded for the disk is precisely because of these bifurcation points that where you have multiple eigenvalues, it's no longer smooth.
Yeah. Okay. Thank you. Thank you for your talk. It was very nice.
Thank you for the question and answer. Does anyone else have questions or comments?
I have a question.
I see.
Go ahead.
Zeev, are you there?
I'm there. We can barely see you.
Yeah, I'm using a
We can hear you.
tablet. I'm probably not using the right technology.
Yeah,
You know, instead of just looking at the gaps between the nth eigenvalues, you could look at some kind of pair correlation function where you look at all possible gaps between all the eigenvalues. Does that make sense? You know, and then you kind of get a dynamical interpretation of the pair correlation function.
No, I know what pair correlation is for, let's say, Neumann or for Dirichlet or for specific.
You can do the cross.
You want to compare two spectra pair, so all
Yeah. You can do the cross correlation function between two different spectra instead of just, you know, taking differences of the eigenvalues for one operator. You take differences of eigenvalues between the two operators. You just don't make it the same index n.
So so I haven't tried to do this. So I prefer to think about the level spacing distribution. So in that sense, you would be asking maybe a question about the distribution of these Robin eigenvalue gaps.
Absolutely, but that's usually a much harder problem, much harder problem.
This is how I started looking at this, and what I conjecture. So in the case of ergodic billiard, the answer is that most of these gaps tend to a constant, and therefore there's no interesting distribution, except if you look at the measure zero set. And for I may be completely wrong here, but let's say in the case of a dispersive, a uniformly hyperbolic billiard, then there is the distribution is a constant. So I don't know if there is a good answer to what you're asking.
Okay.
Thank you.
There was a question here by Nilima Nigam. You want to ask it so everyone can hear?
Oh, for sure. Yeah, thank you. That was a great talk. Thank you.
Thank you.
I was just curious about how the numerics on the stadium domain were done. Was this also a finite element calculation?
Yes, and which is why I only have 200 eigenvalues, and I'm not. So I have to thank Michael Levitin for helping us through this using this finite element package, but he also was very negative about finite element method giving you more than a couple of hundred eigenvalues.
He's correct.
That's okay. That's good to know. But Lijian Chen was here.
Yes.
I see everyone is agreeing and way to bow. They've been using a spectral method.
Okay, good.
A spectral method, and that's how they generated. Let's see this. They generated as of yesterday several about 10,000 of these eigenvalues for the L shape. Now, you can generate 10,000 also with finite element, but they will be garbage. But here for this particular L shape, you can generate 1 million. You will just get noise. But for this L shape, we chose cunningly because inside this L shape has got some inside the spectrum. There's also inside the Neumann spectrum. There's also the Neumann spectrum of this square that's inside, and it accounts for 1/3 of the total spectrum. And I happen to know what the spectrum, Neumann spectrum of the square is. They are integers with very special multiplicities. And so we went and looked for these inside there, and that's how we can tell how accurate the result is. And it's pretty accurate.
Right.
So that was my way of checking. The other way, physicists would use tests for missing levels, but I have fancier methods in this particular example. So here I'm very confident about these 10,000 eigenvalues.
Well, there's a note of caution here as well, because spectral methods, will give you very good accuracy for eigenvalues corresponding to smooth eigenfunctions. But if you have an L-shaped domain in which you have eigenfunctions that become singular as you approach the corner, as you approach the reentrant corner, then the accuracy for those eigenvalues may not be as sharp as it is for the Neumann eigenvalues on the square inside. So that's just a word of caution.
Yeah, I understand that. Again, I'm not an expert, but my way of checking this for the Neumann eigenfunction, a third of them are, as you say, completely smooth, but 2/3 of them are not. And I found the 1/3 of the spectrum with very good accuracy inside these 10,000. This was a bit of an iterative process, of course. Once you know how to check, then you can start fine-tuning. So I'm quite confident about this L-shaped billiard, but we would be happy to have more checks. So this is a special method. I think boundary element method should also be capable of doing it. For instance,
yes.
About some years ago, I wrote a survey for the notices, and then this Alex Barnett was kind enough to produce about 50,000 Dirichlet eigenvalues for this example.
Right.
Using a boundary element method, and I trust him, but he's become like a big boss. Where is he? He's probably not here, so I'm not allowed to badmouth him. But he hasn't risen to the challenge.
No, I respect Alex's work, and these are the kinds of problems in which boundary integral-based methods are actually quite powerful. So yeah, thank you.
Yeah.
There is a question.
Yes, I would like to say something. May I answer? There was a question by Steve Zeldich about the comparison of two spectra with different boundary condition parameters, right? Steve
yeah, pair correlation function.
Yeah, exactly. So then there is in this paper with Martin Zeev, there is a special section on it, which is called parametric spectral statistics. And there we don't answer the question that you exactly answered, but we look at the first and second derivatives of the eigenvalues with respect to the parameter, and we look at that statistics. So you are most welcome to read it. It is a very old paper. It's about 20 years old.
25, if I may.
25, yeah, that's right. Well, you know, at my age, 5 years don't count.
It's within the era of measurement.
Right.
So again, this paper, I recommend. It's not Uzi's job to say this, but I recommend you read it. It's written by physicists, but it's a mathematical paper. They do things which are much more ambitious than what I'm doing here. They actually think of sigma as varying with this eigenvalue in a specific way, hoping to get interesting statistics. This is what started me on the game. And there's a follow-up paper by Mark Dennis and Michael Berry that was mentioned, as I said, by Marco Marletta, where they do some similar things later, but these are much more ambitious than what I've been doing here.
Gregory Berkolaiko, you had a question also?
Yeah, Grisha.
Your mic is off. We don't hear you.
We can't hear you, Grisha. No, still can't hear you. This is the bane of our time. Okay.
I don't know why.
Can you write the question in chat in the meantime? Actually, aren't you next door to Peter Cushman? You can tell him.
So if someone else has a comment or question while Gregory is typing his question, perhaps you can go ahead.
I wanted to say that the isoperimetric is not the right inequality. The right problem is Quinn of Tito's problem.
Which problem?
Length over the area. Isoperimetric is length squared over the area. And you have length for, so it's Quinn of Tito's problem. But still the disk is a solution. But so Igor Wigman corrected me in the chat. Yeah, and there's also like a spectral flow related to changing the sigma, and it's related to like Friedlander's inequalities between Dirichlet and Neumann eigenvalues. So it's also related to this, but I think what you are doing is more quantitative. But
yes, I think so. I think so. So Kolaiko was asking to look at the difference between counting functions, at the statistics of that. So I think that gets swamped out by the remainder term, unfortunately. So I don't know. I don't know how to do this, and the statistics of the Dirichlet to Neumann map. I don't have an answer. I know half of the people here have been working on Spectral eigenvalues, but you know, one of the good things that come from listening to seminars is you learn about new things. So I don't have anything to say about Spectral eigenvalues yet.
Does anyone else have a question or comment for Zeev? If not, let's thank our speaker again. Thank you very much.
Thank you all for your attention.
We will meet again next week for a talk by, where are we? I'm lost in this. By Luigi Provenzano, who will speak about spectral representation of the trace space of H2 and biharmonic Dirichlet problems for multi-parameter Steklov problems. That was a mouthful, but I said it. So have a safe week and see you next week. Thank you very much again.
Thanks again for the talk, Zeev.
Yeah, my pleasure. This was a fun audience. I think the best audience for this talk. Good.
So yeah, I was I was actually wondering, for the most of the results, did you just spare us the difficulty or the results being stated in higher dimension, or is there actually something specific in dimension 2 that you're using in your proof?
For most of them, it works in any dimension, but because I'm either a number theorist or a physicist, so I'm driven by experiments.
Yeah, no, sure. But I mean, sometimes there are specific.
You know, this notion of piecewise smooth is kind of a headache. I understand what it means in
yeah.
dimensions, and there are definition, for instance, in Steve Zelvich's paper, he wrote down the definition. I really didn't want to restrict to the smooth case because you don't have ergodic examples in the smooth case.
Yeah. I see.
It's a theorem. There's a theorem that says for smooth boundary you always have caustics. This is a theorem of Lazutkin.
For smooth boundary, you always have what? Sorry.
Caustics, meaning you cannot be, in particular, you cannot be ergodic. If you have a smooth boundary, you cannot be ergodic.
Isn't the so I guess you don't have infinitely many derivatives for the stadium, right?
For the stadium, you have one derivative, but not two.
Oh, okay.
But you have to have corners. This is why I couldn't restrict to smooth. If I want, I'm driven by actually the ergodic case for me is the most interesting. And you can't restrict it.
Speaking of the stadium, do you think that something similar to what Andrew Hassel has done, where you have where for almost all values of the length you actually do not have QUE? Do you think something similar would tell you that for almost all values of the length, you do see exceptional gap sequences?
That would be a great thing to check.
Yeah, I mean that was the first thing I had in mind when I saw this.
That
result.
would be a very nice thing to try.
Yeah,
that would be very.
Oh, I have 2 remarks.
Yeah,
you could take a disk out of a flat 2 torus. You can probably do experiments with that just as easily. That makes it the exterior of a convex domain, so you don't get this 1/3 into the 1/3 anymore. This is a concave boundary. So
Yeah.
you have no whispering gallery Quasimodes, and this is the C9 billiard, so it's highly ergodic. So that sounds like a good toy model for your thing.
For doing numerics.
Yeah, take a disk out of a flat torus. Just put periodic boundary conditions out of a disk taken out of a rectangle.
Yeah, yeah. I think the numerics here is feasible.
You know, because the result you were quoting is for convex domains. You know, getting these n to the 1/3 thing is what you get for convex, but
no, I needed smoothness, not convex.
This is perfectly smooth. Take a disk out of a torus.
Yeah. So you for that you should get the result they have. This is Barnett Hassel K2 that works. They assume smoothness. Maybe because they didn't want to be bothered with anything else.
By the way, I think Lazutkin's theorem is also for convex domains, isn't it?
No, I thought not. I thought
you don't get whispering gallery Quasimodes. You don't get creeping rays unless you're in the inside of a convex domain. You don't get them outside.
You mean about the lower bound that they have, this whispering gallery mode construction?
About getting, you know, Lazutkin's theorem about getting a Cantor set of invariant curves.
Yeah.
That's for a convex domain.
You're talking about ergodicity, the breakdown of ergodicity.
Yeah, he certainly proved that. Yeah, you get this Cantor set of positive measure. It's a KAM type theorem.
It's a KAM type theorem, exactly.
If the domain is convex, then you have such a thing. I don't know.
Right. Yeah. So I don't know the state of the art without convexity.
Well, you probably don't. You know,
you're saying that for this
exterior,
C9 billiard. You're right. For this C9 billiard with periodic boundary condition, you have chaos. So that's
right. So that's like that's a computable model.
Yeah, I agree. Right. So you don't have to have corners. This is the bottom line. What Steve is saying, and I completely agree.
Right.
Yeah. So I know convexity was an issue. In particular, your paper, Steve. With Andy Hassel, initially it was under convexity assumption, this boundary ergodicity, then you removed it.
Oh, you know, that's this. We use the technique which the physicists use. I'm sure Smolanski, if he's still around, knows this very well. You use these boundary layer potential arguments. And the problem is that their critical points include the billiard trajectories, which go outside the domain, then back in again. They're called ghost orbits.
Mm-hmm.
So if you don't do an intrinsic thing, if you try to write down an intrinsic parametric, which does not use that it's a domain in the plane, like Chazarin, then you don't have these orbits occurring. You know they cannot play a role in any trace formula. But a priori, they do occur if you try to use the Balian and Bloch technique. And then you have to get rid of them. That's like talk about a major hassle in my paper with Hassel.
Yeah. But eventually you got rid of it.